Welcome back, students, to Unit 11, Acid-Base Chemistry. Today we'll be going into Unit 11.2, Acid-Base Theory, and the pH scale. In the first unit, we introduced acids and bases to you using a very simple definition, that an acid is an ionic compound whose formula starts with a hydrogen, and a base is an ionic compound whose formula ends in hydroxide. However, acids have long been characterized based on how they react. For example, solutions that react with metal and produce hydrogen gas we knew to be acidic. Acids, therefore, are corrosive. Those hydrogen ions are able to pull electrons off things and pull them apart on an atomic level. Acids, however, in low concentrations can be used to give flavors to certain things. Acidity is often attributed to the sour taste in things. So foods such as lemons contain citric acid, carbonic acid in soda, and it's those acids that impart that flavor to them. In fact, it's these acids in those foods that make them bad for your teeth. The additional carbonic acid in soda, for example, reacts with the calcium carbonate of your teeth to degrade them. They are corrosive. They eat away at your teeth. In 8th grade, you were probably introduced to the fact that acids turn litmus paper a shade of pink or red. And because acids have hydrogen ions, which are free and mobile, acids are conductors of electricity. These hydrogen ions can be thought of as electrolytes. Bases, on the other hand, taste bitter. So solutions such as beer, ethanol contains a hydroxyl group, which impart a basic characteristic to beer. Bleach is another example of a base. If you've ever felt bleach, you know that it is a very slippery substance. That being said, if you ever do get bleach on yourself, please make sure to rinse it off immediately because it is a base. It is caustic. It will begin reacting with the fats in your skin. Bases turn litmus paper a bluish color, and because bases are ionic compounds consisting of a metal cation and a hydroxide ion, bases also conduct electricity. With that being said, you're able to answer your first note quiz question. Please pause the video and make a note in the back of your packet for your first note quiz question. Now, the definition of an acid or a base that we have been working on is known as the Arrhenius definition of an acid. Arrhenius said that an acid is any substance that ionizes to produce hydrogen ions. So, for example, hydrochloric acid breaks down into hydrogen ions and the chloride ion. That hydrogen ion makes hydronium, again, which is the same as hydrogen ions. Arrhenius said that a base is anything that ionizes to produce hydroxide. So the definition we had been using, that a base is some metal ion and a hydroxide, encompass things like sodium hydroxide or calcium hydroxide, or transition metals like chromium 4 hydroxide, all of which are bases according to Arrhenius. However, Arrhenius' definition is not all-encompassing. In the previous unit, we said ammonia is a base, and you're expected to know it's a base. But ammonia does not contain a hydroxide ion. So how is ammonia a base? Well, that question plagued chemistry for several years. And it wasn't until the work of Bronsted and Lowry that we came up with a different definition of acids and bases. Bronsted and Lowry were two scientists who were interested in why ammonia would cause a solution to produce hydroxide ions. In order for it to make sense for ammonia to produce hydroxide, ammonia would have to accept a hydrogen from a water molecule, making it a proton acceptor. So Bronsted and Lowry say that a base is any substance that accepts protons, because all a hydrogen ion is a proton. By donating a proton, water is acting as an acid. However, these reactions are set up in equilibrium. So, at the same time that water and ammonia are colliding, they are producing hydroxide and ammonium. Ammonium and hydroxide can collide to produce ammonia and water. However, the reverse reaction occurs in which ammonia donates a hydrogen ion to hydroxide. So in the reverse reaction, ammonium, being a proton donator, is acting as an acid, and hydroxide is acting as the base. Meaning that we end up with something that acts as an acid, the water, acting as an acid in the forward reaction, acts as a base in the reverse reaction. These are known as conjugate pairs. Water becoming hydroxide, and ammonia becoming ammonium is its conjugate acid. So acid-base conjugate pairs are simply what something is acting like in the forward reaction versus what it is in the reverse reaction. If I ever ask you for the conjugate base of something, it simply means remove a hydrogen. If I ask you for the conjugate acid, it means add a hydrogen to it. You'll notice that water can act as both an acid or a base. This is because water is one of a couple substances that is what's known as amphoteric. It can be both an acid or a base. Let's get some practice showing the movement of hydrogen ions, determining which is an acid and which substance is a base, as well as our conjugate acid-base pairs. In your packets, find example 5. Here we have oxalic acid reacting with ammonia to produce bioxalate and ammonium. The only way that oxalic acid can produce bioxalate would be by it donating a hydrogen ion to the ammonia. In order for ammonia to become ammonium, it would have to accept that hydrogen ion. So in the forward reaction, oxalic acid is acting as an acid. And by accepting that hydrogen ion, ammonia is acting as a base. In the reverse reaction, however, in order for bioxalate to become oxalic acid, it would have to accept a hydrogen ion from the ammonium. So in the reverse reaction, ammonium is acting as an acid, donating a proton. In the reverse reaction, bioxalate accepts that hydrogen, so it is a base in the reverse reaction. Your conjugate acid-base pairs are simply when a species, such as the oxalate ion, becomes either bioxalate or oxalic acid. The conjugate base pairs, conjugate acid-base pairs for ammonia would be when ammonia forms ammonium or ammonium forms ammonia. When bisulfate becomes a sulfate, it donates a hydrogen ion to water. So water, being a proton acceptor, is acting as a base. And bisulfate, donating that proton, is acting as an acid. In order for sulfate to go back to being bisulfate, it would have to accept a proton from the hydronium ion. Therefore, by accepting a proton, it's acting as a base. The hydronium ion donating that proton is acting as an acid. Your conjugate pairs, therefore, are bisulfate becoming sulfate and sulfate becoming bisulfate, or water becoming hydronium and hydronium becoming water. You're now able to answer note quiz questions 2 and 3. Again, in the back of your packet, make note of which answers you choose, and at the end of the video, record those answers in the Google form provided. You're also able to do page 10 in your packet. When doing page 10, number 1 shows water acting as both an acid or a base. It often helps to distinguish one water to be the water that forms the hydroxide and one water to be the water that forms the hydronium. So why don't we label this first water, water X, the one that becomes the hydronium. And we'll say water Y, the second one, is the one that becomes the hydroxide. So with that in mind, you should be able to finish page 10 in your packet. Please pause the video and do so now. Bronsted-Lowry's definition of an acid and a base is the most commonly tested form. You will receive questions that ask you to identify something as an acid or a base based on Bronsted-Lowry's definitions. You will also be asked to identify an acid or a base based on Arrhenius's definitions. Again, remember those are the simple ones. Starts with a hydrogen, it's an acid. Ends in hydroxide, it's a base. However, these definitions cannot explain why ammonia, a known Lewis base, can neutralize another substance, boron trifluoride, which for some reason is an acid. Boron trifluoride, or boron with 3 of anything, is an acid. It causes a solution to become acidic. However, Bronsted-Lowry's definition does not provide an example for why this is. So, another scientist, Albert Lewis, came along and provided a theory as to why some substances are acids, even though they don't fit Bronsted-Lowry's definition or Arrhenius's. Albert Lewis is the same person who gave us the Lewis dot diagrams. This, therefore, has a lot to do with the shape and geometry of molecules. Lewis found that an acid is an electron pair acceptor because donating a proton and accepting an electron has the same net reaction. The atom becomes more negative. So acids are simply electron pair acceptors, while bases are electron pair donators. Boron trifluoride, therefore, reacts with ammonia by accepting the lone pair of electrons on that nitrogen atom, forming what's known as a coordinate covalent bond, in which one atom, the nitrogen, provides all the electrons in the bonded pair. In all likelihood, you will not receive very many questions that deal with a Lewis acid or base. In fact, it won't be until second year chemistry and AP chemistry where you even ask a single question about this. However, because I'm not such a nice guy, you can expect on your test for me to ask you, what is an example of a Lewis acid? Boron with 3 of anything is the classic example of a Lewis acid. So please expect that question to show up on your test just as it is in your homework. When we talk about the strength of an acid or a base, we are talking about how it breaks up in solution. A strong acid breaks up completely in solution. So for example, hydrochloric acid, when placed in water, every single chloride is separated from its hydrogen counterpart, meaning all of these chlorides produced a hydronium ion. There are very few strong acids in reality in which every molecule of acid produces a hydronium ion, and there are very few strong bases in which every hydroxide is released from its metal cation. When we say that an acid is strong, we are in fact talking about its ability to conduct electricity, much like when we said we have strong electrolytes. Those were electrolytes that produced lots of metal cations that could conduct electricity and therefore would light up a light bulb well, would conduct energy well, because you have lots of mobile free ions. Strong acids produce lots of mobile hydronium ions, and these hydroniums can complete a circuit, so strong acids are also strong electrolytes. Weak acids are not less dangerous than strong acids, they simply conduct electricity weaker. Very few of them produce hydronium ions. For example, acetic acid or vinegar, very few acetic acid molecules produce a hydronium ion. Most of the hydrogens stay with their acetate anion. With that being said, you can answer your next note quiz question. Please do so, notes in the back of your packet, and answer it in the Google form at the end of the video. Solutions are often characterized as being acidic or basic based off of their pH, or potential hydrogen. If a solution has a pH of less than 7, it is known as an acid. If it has a pH greater than 7, it is known as a base. And these scales denote higher or lower concentrations of acid or base. So something with a very low pH is either a strong acid or heavily concentrated. Something with a very high pH is either a very strong base or heavily concentrated. You can think of the pH scale as being the number of decimal places in front of that concentration. Something with a pH of 0 you can think of as there are 0 decimal places in front of the concentration of hydrogen ions. So there are a lot of hydrogen ions in solution. Something with a pH of 13 has 13 zeros in front of the concentration of hydrogen ions. And therefore there are very few hydrogen ions in solution. Working with these very, very small or very, very large numbers is problematic, so we have a shorthand for that, and that's where the pH scale comes into play. Once you finish question 5, you can also answer question 6 and 7 and 8 in your packet at the end. Please note those answers so at the end of the video you're able to record them in the Google form. The pH scale is based off of the fact that water self-ionizes, and at room temperature only 1 in every 10 million water molecules undergo this process, meaning at room temperature there's 1 times 10 to the negative 7th molar hydrogen and hydroxide ions. In the last unit we talked about equilibrium expressions, so therefore the equilibrium constant for this reaction is 1 times 10 to the negative 14th. And it's a constant. So if I know the hydroxide concentration or if I know the hydrogen ion concentration, I can determine the other using this value. Because at room temperature, and we are going to assume all reactions for this unit occur at room temperature, together the concentration of hydrogen and the concentration of hydroxide have to equal 1 times 10 to the negative 14th. Now, the pH scale is based off the negative log of the concentration of hydrogen, but it's not just that. P denotes the potential of something. So you don't just have a pH scale, you can also have a pOH scale. It would simply be the negative log of the concentration of hydroxide, and the two run opposite one another. Something with a high pH has a very low pOH. Something with a high pH has a very low pOH. We can even use this on our equilibrium expression for the self-ionization of water, that together your concentration of hydrogen and hydroxide has to equal 1 times 10 to the negative 14th. Well, if you were to take the log of both sides, specifically the negative log, to determine the P of that thing, you would find that the pH and the pOH has to equal 14. So if I know the pH, I can find the pOH by subtracting from 14. So let's do just that. If I know the concentration of hydrogen ions, I can find the pH. I can use that to find the pOH. So find example 6 in your packet and grab a calculator. So if the concentration of hydrogen ions is 1 times 10 to the negative 4th, we can find the pH directly, because pH is simply the negative log of the concentration of the hydrogen ions. So if we take the negative log of 1 times 10 to the minus 4th, we'll find our pH. So, grabbing a calculator, we'll type in the negative log of 1 times 10 to the negative 4th, and get that the pH is 4. The pOH would simply be that equilibrium constant of water, 14, minus the pH. Since our pH is a known value, we just found it to be 4. We're simply going to do 14 minus 4 to find that the pOH is 10. And though this question doesn't ask it, you should be able to tell me if this solution is acidic, basic, or neutral. A pH of 4 is less than 7, so this is an acid. Or the concentration of our hydrogen ions is greater than the concentration of our hydroxide ions. Because remember, P something simply means the number of decimal places before that concentration. So 4 decimal places, something in the millionths place, is a lot more concentrated than something in the, I don't even know what decimal place you would call this. If a solution has a concentration of hydroxide ions that's 1 times 10 to the minus second, we can determine its pH and pOH as well. The easiest one to figure out first would be to find the pOH. Since I have the concentration of hydroxide, I should solve for the pOH, which would be the negative log of the concentration of the hydroxide ions. So the negative log of 1 times 10 to the minus second. So I grab my calculator, and the negative log of 1 times 10 to the negative second is 2. So our pOH is 2. pH, therefore, just has to be the equilibrium constant of water, 14, minus our pOH, which we just found to be 2. So 14 minus 2 will tell me my pH, so my pH is 12. Again, based off of these numbers, you should be able to tell me if a solution is acidic, basic, or neutral. So a pH of 12 is more than 7, so this is a base. Or again, you can think of P as the number of decimal places in front of that concentration. So we have more hydroxide, this is a base. There is a shortcut, especially if the coefficient of your concentration is 1. And that simply is that the negative exponent is the P something. So the pH would be the negative of negative 4. And the pOH would simply be 14 minus that. Or here, since this is 1, the negative of negative 2 is 2, giving us a pOH of 2. This, however, only works if your coefficient is 1. You can just eyeball to get close to an answer to say probably the pH of this is somewhere near 10, but this coefficient is going to make that not 100% true. It's going to be close to 10, but it's not going to be 10. The pOH here will be close to 14, but it's not going to be exactly 14 because this coefficient is going to change that. So keep that in mind that you will need a calculator if you do not have a coefficient that is 1 for your concentrations. That being said, let's continue example 6. If the concentration of hydrogen ions is 3.8 times 10 to the negative 10th, that means that the pH is simply the negative log of 3.8 times 10 to the negative 10th. So we'll grab our calculator and type in the negative log of 3.8 times 10 to the negative 10th. And again, we expect a number that's near 10, and while 9 is close, it's not that close. So again, general rules of thumb. So we get that the pH is 9.4. The pOH is simply 14 minus that. pOH would be 14 minus 9.4. So 14 minus our answer would tell us that the pOH is 4.6. Again, you can either think of it in terms of number of decimal places, in terms of the concentration, or simply The pH is greater than 7, so this is a base, because we have more hydroxide than we do hydrogen. Lastly, if our concentration of hydroxide is 7.9 times 10 to the minus 14th, we can find our pOH by taking the negative log of that number, 7.9 times 10 to the minus 14th. We expect a number that's near 14. Let's see what we find. The negative log of 7.9 times 10 to the negative 14th. And we get 13. Again, we can rough estimate, but we're not going to get it 100% right. 13.1 is our pOH. Our pH is simply 14 minus that 13.1. So our pH, 14 minus our answer is 0.9. A pH of less than 7 is an acid, or there are very few decimal places before our concentration. So we have way more hydrogen than we do hydroxide, making this an acid. Again, acids have more hydrogen ions than hydroxides. So anything with a pH of less than 7 is an acid. Anything that has more hydroxides than hydrogen ions is a base. And neutral solutions are those found exactly in the middle, exactly 7. You can go backwards from the pH to the concentrations by taking the anti-log. So pH, or P anything, is simply the negative log of whatever we're talking about. So pH would be the negative log of the concentration of hydrogen ions. In order to run backwards to find the concentration of hydrogen ions, to solve for this, we can first move the negative to the opposite side by multiplying both sides by a -1, giving us the negative pH equals the log of the concentration of hydrogen ions. To undo a log, you simply raise the base of that log. As it's not noted here, these logs are base 10. So we will raise 10 to the negative pH to get rid of the log, solving for the concentration of the hydrogen ions. Again, that's just to find the hydrogen ions because we were given the pH. If we want the hydroxide ions, we would have to use the pOH and the concentration of hydroxide ions. So with a pH of 6, we can solve for the concentration of hydrogen ions by taking 10 to the negative pH. So 10 to the negative 6 will tell us the concentration of hydrogen ion. So in our calculator, if you hit second log, the calculator will undo a base 10 log. So by putting in the anti-log to the negative pH, we can find that our concentration of hydrogen ions is 1 times 10 to the -6. To find the concentration of hydroxides, we could go through the equilibrium constant, 1 times 10 to the -14th, has to equal these two when multiplied. Personally, however, I find that to be a lot of math, and exponents can be scary. So instead, personally, I prefer to find the pOH and simply repeat the process, replacing H with OH to find the one I'm missing. So personally, I would say take the pH and do 14 minus the pH to find the pOH. 14 minus 6 is 8. So the concentration of hydroxide ion is simply to take the anti-log of -8. So our concentration of hydroxide ions is 1 times 10 to the -8. Again, because these were whole number pHs, our coefficient was simply 1, and then times 10 to whatever the negative pH is. But if our pH is a decimal place, such as the case with the next one, it doesn't work out as nicely. For that, you will have to use a calculator, but the process is the same. Here, we're given the pOH. So we can find the concentration of hydroxide first by simply doing the 10 to the negative pOH. So 10, the antilog of negative 10.4 would give us our concentration of hydroxide, which is 3.98 times 10 to the minus 11th. And it's a concentration, so probably molar. To find the concentration of hydrogen ions, we will need the pH. Concentration of hydrogen ions would equal 10 to the negative pH. So the pH, therefore, is simply 14 minus the pOH. So in our calculator, if we do 14 minus 10.4, we get that the pH is 3.6. So the concentration of hydrogen ions would simply be the antilog of that number. And we get that the concentration of hydrogen ions is 2.51 times 10 to the minus 4th molar. With that, you are able to answer question 9 in your note quiz questions. Please pause the video, make note of your answer, and at the end of the video, record that answer in the Google form. You're also able to complete page 12 in your packet. Page 12 is fairly straightforward and simple. I give you one piece of information and expect you to find all the others. Please pause the video and do page 12 at this time. Lastly, acids and bases are categorized as being mono or polyprotic, depending on how many hydrogen or hydroxides they have to donate. Will change their pH in solution. So for example, hydrochloric acid is monoprotic. It has only one hydrogen to give off, meaning for each one hydrochloric acid, I get one hydrogen and one chloride. Acetic acid is also monoprotic because the acetate ion will not dissociate from one another. It is only this first hydrogen that can be removed, giving us a hydrogen ion and the acetate ion. Polyprotic acids and polyprotic bases are different in the fact that they can donate more than one hydrogen or hydroxide. So for example, calcium hydroxide can donate 2 hydroxides when it dissociates, and therefore it would double the concentration of hydroxide in solution, greatly changing the pH and the pOH. Sulfuric acid is also polyprotic. I can receive 2 hydrogens for each molecule of sulfuric acid that dissociates. Thus, the concentration of hydrogen ions would be twice as much when it dissociated. With that being said, you're finally able to answer the final note quiz question. Make sure you make note of this at the end of your packet and record your answers in the Google form. You're also now able to do page 13 and 14 in your packet. On page 13, I provide you the concentration of an acid. You first have to figure out if it's mono or polyprotic. Change its concentration accordingly when you dissociate it, and then find the pH or pOH. On page 14, I provide you the pH and I ask you for the concentration of hydrogen ions and hydroxide ions. And that is nothing new, we've already done that. With that being said, please make sure you complete page 13 and 14 in your packet. Next class, we will take a quiz where I will ask you to label the Bronston-Lowry acid and base, as well as name an acid or a base. You'll then have to find the pH of a solution and find its concentration of hydroxide ions given that pH. I will end the quiz by asking you to find the pOH. Please study, and next class we will talk about neutralization reactions and titrations, 11.3.